Okay, that the definition of what we mean by a positive operator. So self-adjoint operator T is called positive if this condition holds for all x belongs to H. That's important. And the next thing is that let T1 and T2 be self-adjoint operators. We write T1 greater than equal to T2 if T1 minus T2 is positive. What does it mean? Well, it means that instead of T, I substitute T1 minus T2 and that's greater than equal to 0. But another handy notation for that would also be that T1 minus T1 greater than T2 also implies for all values of x belong to capital H. The next topic that we come to is that of an orthogonal projection. So an orthogonal projection E on a complex Hilbert space is positive since there are two properties of orthogonal projection. First is that they're idempotent and the second one is they are self-adjoint. Now what they're saying that every orthogonal projection E on a complex Hilbert space H is positive since the inner product of Ex with Ex. Now since it's idempotent, since it's self-adjoint, since this is how the norm is defined and norm is always greater than equal to 0. Now let H be a complex Hilbert space and let Tn be a monotone decreasing sequence of positive self-adjoint operators. The sequence Tn converges pointwise to a positive self-adjoint operator T which belongs to LH. Furthermore, T is less than equals to Tn for all n belong to capital N. So if you give me a monotone decreasing sequence which is bounded below, then it converges. If I have a monotone decreasing sequence of real numbers such that it is bounded below, then I know that it converges. And similarly in the case of monotone decreasing sequence of positive self-joint operators. So when we are doing functional calculus, we need to see the beauty behind it, that results which were true for functions which used to take real numbers as arguments. Now also some of them, not all of them, also hold true for functions which take an operators as argument. So in this particular case, what we are seeing is that the way we used to define limits, and we used to say that, okay, if I have a convergence sequence which is bounded below, then the point to which that it converges, for example, if I have xn, which is my convergence sequence, and it converges to x, such that this is bounded below, which means that the x is the infimum of it. So I always used to have that this infimum is always less than equal to any particular element of my sequence. The thing is that the same kind of calculation I can do in the case of positive self-adjoint operators. I can say that this T is less than equals to Tn for all n belong to capital N. But this less than is meant in the sense of the less than that I defined, that I can say that Tx comma x is less than equals to Tnx comma x for all x belong to capital X or capital H in our case. Now the second lemma tells me that if I have the sequence of self-adjoint operators which converge pointwise to self-adjoint operators. So by converging pointwise, I just mean that limit n tending to infinity Sn x is equals to S of x. So this Snx is a sequence of numbers. I have S1, x, S2x, S till Snx, and it goes on. Now this converges to S of x pointwise. That's what the meaning of this is. So if we converse pointwise to self-adjoint operators and alpha and beta belong to the set of complex numbers, it follows that alpha Sn plus beta Tn converges pointwise to alpha S plus beta T, and Sn Tn converges pointwise to St. So this is just the lemma of it, and it's showing that these operators converge pointwise. Now the next thing that we're gonna see is this proposition, which shows that let H be a complex Hilbert space, let T be a self-adjoint operator, and F be a non-negative continuous function. Non-negative is important. It follows that Ft is positive. Well, the proof is define the non-negative continuous function g by, so I have a function g and I define the non-negative continuous function. Why this is non-negative? Because I say that, well, in order to prove that f of t is positive, I need to take this step. I need to define yet another non-negative continuous function. What I do is that I take the under root of f of x, since I know that f of x is positive. Now this f of x, I call, if you look at the definition above, they call that this f of s is non-negative continuous function. Now what they mean by this f to be non-negative continuous function is that f of x gives me a real value which is always greater than 0 for every value of x belong to my Hilbert space H. Now when I say ft is positive, I mean it is positive as an operator. Now what we did was we defined a non-negative continuous function like this. We show that, okay, f is equals to g square since f of t is equals to g of t square. And next we find it out that, okay, if t is self-adjoint, then f of t is self-adjoint, then this function itself is also self-adjoint. And then I can say that this thing here is equals to this thing, which is equals to this step of self-adjointness, and this simply norm, which is always greater than equal to 0. Okay, the next thing that we do is again simple corollary. We make use of the proposition given above. We say that let H be a complex Hilbert space, T be a self-adjoint operator, and F and F2 be continuous functions, such that F1 is always greater than F2. Now this is pointwise. It follows that F1t is greater than equal to F2t. Now F1 minus is, now this thing that F1 is greater than equals to F2, it just means that F1x is greater than equal to F2x for every value of x belong to capital H. And we use, or we make use of this proposition. We say that, okay, if we say that f1 is always greater than equals to f2, then f1 minus f2 is always a non-negative continuous function. Now we can say that f1 minus f2 t is positive, and then when I take the definition of f1 minus f2t is positive, I can definitely say that f1t is greater than equal to f2t. So now we are going to do a final overview of the chapter on self-adjoint operators in Hilbert spaces. So you have to keep in mind that now I will just focus on the definitions and the theorems. I will not go to the proofs of them. I'll just give you the basic and the most important ideas in self-adjoint operators without explicitly going through the proofs of them. So the idea is that let H be a Hilbert space, and a family E lambda parameterized by lambda is called resolution of the identity if it has the following properties. So what are the properties? The properties are that E lambda is an orthogonal projection for each lambda belonging to R. Now, orthogonal projection means that it is idempotent and self-adjoint. Now, idempotent is simply p square equals to p. This is this notion of positiveness that E lambda is less than equals to E mu for lambda less than equals to mu. This is the second notion. Third thing about is that limit lambda tending to minus infinity E lambda is equals to 0, and limit E lambda tending to plus infinity is I pointwise. That is important. And the last thing is continuity from above. We say that epsilon tends to 0 from above. This is what I mean when I write it like this. And E of lambda plus epsilon is equals to lambda plus epsilon, again pointwise, for every lambda belongs to R. What is E lambda? E lambda is resolution of the identity. It is an operator which follows these four properties, okay, that we have seen till now. Now the next addition to the concept is that when I have a Hilbert space and I have T as my self-adjoint operator, now a resolution of identity which we just saw above with the properties that E lambda is equals to 0 if lambda is less than m, and E lambda equals to I for lambda greater than equal to m, and this. So if I have a ROI and which satisfies these two properties, then that ROI is called spectral family for T. Now if you look above, there was no mention of T before. When we did resolution of identity, there was just some operator defined on a Hilbert space H which has those four properties. Now we make an addition we say that let H be a Hilbert space, let T be a self-adjoint operator. And now a resolution of identity with these properties is called a spectral family for T. That's the idea here. Now the next thing that we look is the Riemann-Stieltjes integral. The Riemann-Stieltjes integral is basically a way to take integrals. I have a function defined on AB to C, and similarly I have a function g defined on AB to X, and X be a non-trivial complex Banach space, and F and G be functions. Now Z be a partition of AB where delta Z is equals to the max of these values, and SFC be the Riemann sum. So what is the Riemann sum? Essentially the Riemann sum is, so you have a function evaluated at a point. Yeah, this is basically the picture, and a little nice picture of what we are talking about. We are basically taking these rectangles and adding all of them up, but it's a very naive way to see them, because earlier when I used to do f of x dx, and I used to do the integral of this, so that dx used to be this small strip here, dx used to be this strip, and then I used to take f of it, and then used to do the whole sum of everything here, and then we used to get like these different strips. So the idea remains the same, but rather than this dx, I can also have d of gx, which we will see in the future. So basically the Riemann-Stieltjes integral is given by this formula. So all you need to know is this formula, and I think by just looking at this equation we can get a basic intuition about what the Riemann-Stieltjes integral is trying to do. So this is essentially the whole idea behind it. You take the Riemann sum and then you say that delta Z tending to 0, and then you evaluate the whole thing. Now let H be a Hilbert space and T belong to LH be a self-adjoint operator. Now E lambda be a spectral family for T. It follows that T can be reconstructed like this. So the thing is that this T does not depend on delta. Another thing about this T is that if I know E lambda, the spectral family, I can find T. I can reconstruct this T from my spectral family. And this integral converges in LHH, not pointwise. This also gives an operator in LHH. So the essential idea behind this is I have a Hilbert space and I have a self-adjoint operator T, and I say that if E lambda is a spectral family for T, then T can be reconstructed in this way.
So the only thing I want to add here is that this lambda dE lambda can be expanded in this form, and what next can be done is that this integral it converges in LHH. So what it would give me is an operator in LHH, and this can be written like this here. One very subtle thing I would like to discuss with you guys is that why there is m minus delta here and there's a capital M here. Now the reason behind this is, if you go up and look at property number 4 for my resolution of identity, it said that this limit as epsilon goes to 0 from the positive size is equals to E lambda. Now if I hadn't had this limit, then I could have easily written small m to capital M, but since I know that there is this condition on this, so since E is continuous only from one side, it causes problem when considering the integral. Now what to do? Now consider this. If you have a function defined on the closed interval AB, now what spectral family or what resolution of identity tells us is that this is continuous in this direction, no? But it's this direction which is causing the problems. It's always continuous this way, because now we are taking epsilon to 0 from the positive side, but here it's not continuous from this way, and that is the reason why we need to take m minus delta. So in summary, all we need to remember is that because of property number 4, my function is continuous. So if my function is defined on interval a and b, it needs to be continuous from this side as well as this side. I know that my function is continuous from this side, but here we run into some problem. That's why we take m minus delta. And if it would have been, if you see in condition number 4, if it would have been epsilon just going to 0, not just from the positive side, if we see here, if it would have been just epsilon going to 0, then I wouldn't have needed that condition. Now again, I would have, suppose it would have been just epsilon going to 0, then I would just integrate from small m to capital M, and if it was epsilon going to 0 from the negative side, then I have to take m plus delta for the same reasons given.
So next thing that we study is that H be a Hilbert space, T be a self-adjoint operator, then E lambda is a resolution of identity, and not then. So I have Hilbert space, I have T as a self-adjoint operator on my Hilbert space, and I have E lambda, which is a resolution of the identity with this formula.
One important detail, it's that I did not say that E lambda is a resolution of the identity which is a spectral family of T. However, I did say that E lambda is a resolution of the identity and T is given by this formula. Now you know that if E lambda is a spectral family of T, then T would be given by this formula. But it could be possible that another resolution of the identity can construct T with this formula. So the summary is, suppose you have a resolution of the identity given, and suppose that T is given by this formula. Now all I'm saying is that if these two conditions hold, then f of t would be given by this formula.
One more thing, I have an f, which is a continuous function. Then f of t is given this way. So earlier I saw in functional calculus that I used to take the limit of the polynomial tending to infinity, and I used to define ft. But now I'm saying that, okay, I have a Hilbert space, I have a self-adjoint operator t. Now I have resolution of an identity such that t is equals to this integral. And then if I have a continuous function, then I can take f of t and I can define it in this way. And
one minute detail regarding what we did just now is that I can take this definition pointwise also. So earlier I was evaluating f of t with the help of this integral, but this x was missing. It was just t of e lambda. Now I can evaluate this integral pointwise also, and same I can do in terms of the inner product also. So if you look at this formula and this formula, you can see what I'm trying to say.
The next thing that I have is, let H be a Hilbert space and T be a self-adjoint operator, E be a resolution of the identity with this property. Then it follows that E lambda is equal to limit n tending to infinity f n mu t equals to, is pointwise for each mu belonging to R. So what I'm saying that, okay, so the thing that we have to keep in mind is that the function is this f has to be this function. It has to be, it cannot be something else. I have the resolution from identity, and with the property that t can be written like this, then I can say that, okay, E mu or E lambda has to be given like this. And the last thing that I would like to discuss is, now if you make a summary of what we have done till now, we have said that, okay, we have said that we have defined the definition of, we have defined resolution of identity. We have said that, okay, if resolution of identity has some special properties, then this resolution of identity is a spectral family for T. The next thing that we say that E lambda is a spectral family for T, then T can be reconstructed with this formula. The next thing I can say is that, okay, if E lambda is a resolution of identity, and T is self-adjoint with this formula, then an f be a continuous function, then it follows that f of t can be given like this. The next thing I say that, okay, if E lambda is a resolution of the identity and T is self-adjoint with this formula, see, then I say that, okay, E mu can be calculated with this limit. Now, and this limit is pointwise. The last thing that I would like to say that is that every T has a spectral family. So all my previous theorems were based on if T is a self-adjoint operator which has a spectral family if T. So in essentially this remark, I have to show that, okay, if T has a spectral family E mu, then it is necessarily given like this. It is unique. So all spectral families are unique. And if T is self-adjoint and if T has a spectral family, then this spectral family is necessarily given by this. So which means that it is unique. So spectral families are unique. Let me just write it down. Now, the last theorem that I would like to say is that every T has a spectral family. So, let H be a Hilbert space, T be a self-adjoint operator. The formula E mu defines a spectral family E mu for T. So, this is essentially saying that every T has a spectral family. And I say that the last corollary is if let T be a Hilbert space and T be a self-adjoint operator, then the resolution of the identity is the spectral family of T if and only if this T is given like this.
So finally, we do a quick recap of all the topics we have covered. So we have seen what resolution of identity means. We have given it a definition with those four properties. And then we say that if this resolution of identity has certain extra properties which has to do with the self-adjoint T, then E lambda is a spectral family of T. So now we have defined what a spectral family means. And then we say that if E lambda is a spectral family for T, then T can be reconstructed by this formula. Then we say that if E lambda is a resolution of an identity and T is given by this, you see, I am not saying here that E lambda is a spectral family of T, because if I know that if E lambda is a spectral family of T, then T can of course be given by this formula. Here I am weakening this condition a bit. I am saying that E lambda is just a resolution of an identity and T is given by this formula. And I have f, which is a continuous function between small m and capital M. Then with functional calculus I can write f of t in this way, in this form. Okay, so I can define f of t as this. And then I say that if E lambda is a resolution of an identity and T is self-adjoint with this formula, then the limit exists. Which limit? This limit. The limit given in this formula. We say that the limit exists and it converges to E lambda. So now why does the limit exist and why it converges to E lambda? So we know that this f and lambda is continuous, so that f and lambda t is defined because of functional calculus, and it is a self-adjoint operator. And the sequence f n lambda t pointwise is monotone decreasing and bounded above. And we know that if Tn be a monotone decreasing sequence of positive self-adjoint operators, the sequence Tn converges pointwise to a positive self-adjoint operator T belonging to the space LH. Furthermore, T is less than or equal to Tn for all n belonging to natural numbers. So this property we have seen, and thus we can say that the limit exists. And now the theorem is that this limit is equals to E lambda. So we don't prove why this limit is equal to E lambda, but for an understanding point of view, we can say that if we have a monotone decreasing sequence of positive self-adjoint operators, so we know that f and lambda t is positive and self-adjoint, then we can say that the sequence converges pointwise to a positive self-adjoint operator, which is given by E lambda. Okay, so now we have this, and hence now we connect all those ideas. We say that if T has a spectral family, then it must be given by this formula. So earlier we had that if E lambda is a resolution of identity and T is self-adjoint with this property, then E lambda is given with this formula. And now I am saying that if T has a spectral family, then it must be given by this formula. So I am asserting that these spectral families are unique. And finally, summing it all up together, I can say that every T has a spectral family. So I'm saying that let T be a self-adjoint operator, then E lambda given by this formula defines a spectral family for T. So this is how I sum up everything. So starting with starting with this proposition saying that if E lambda is a spectral family for T, then T is given by this. Then I'm saying that if E lambda is a resolution of identity and T is given with this formula, then I can say that E lambda is given by this formula, and still this E lambda is a resolution of identity. And then I'm saying that this spectral family E lambda, if T has a spectral family, then it must be given by this formula. And finally I'm saying that every self-adjoint operator T has a spectral family and it is given by this formula.